Hello and welcome to the lecture number 2 in our course 2 series of lectures on geometrical and physical optics. The title of this lecture is Image Formation in Mirrors. So the main topic of this lecture is going to be analysis of the mirrors. Mirror is an important optical component. We are going to be analyzing and tracing the propagation of light through this important optical component. We're going to learn about so-called rays tracing method. We are going to be learning about the mirror formula, and finally at the end of this lecture we're going to also be looking at some of the applications of the mirrors. After finishing this lecture, you will be able to describe what is meant by Gaussian and paraxial optics. You will be able to describe the relationship between collimated light and the focal points of the convex and concave mirrors. You will learn how to use the ray tracing techniques to locate the images formed by the plane and curved mirrors. And finally, you are going to be also able to use the mirror equations and mirror formula to determine location, size, orientation and nature of images formed by the spherical mirrors. As already mentioned, the main topic of this lecture is going to be the mirrors. We are going to be looking into two different types of mirrors, plane mirrors and spherical mirrors, where spherical mirrors are going to be either convex or concave. The main purpose of a mirror is to produce a 3D image of a 3D object, and in this lecture we are going to learn how to properly figure out the size, orientation and the location of the image based on the information about the location and size of the original. We are going to be using the law of reflection. So the law of reflection is going to be at the core of the analysis that we are going to do with the mirrors. We are going to be using two different techniques, one being geometrical ray tracing technique and another one is going to be calculation based on so-called mirror formula. So again, we will be able to locate the image in the mirror either graphically using the ray tracing technique or analytically using mathematical formulas that are going to enable us to locate the location and the size of the images produced by a mirror. Images with the mirrors are formed when many non-parallel rays from a given point on a source are reflected from the mirror surface, and they would converge and form a corresponding image point. On the picture on the right hand side, you can see this concept applied to a few objects. So if you're going to start with a picture A, we can see that we have an original shown here as a point S, and that point S is going to reflect and produce the mirror image S prime. And you can see here a whole bunch of different light rays. Some of them are incident light rays that are originating from the point S, and then they are being reflected as reflected light rays. And you can see that if you extend these light rays, these reflected light rays, they are going to be eventually merging into one single point, and that one single point that's shown here as S prime represents the mirror image of our point S. The same concept can be applied on the objects that are not just of a one-dimensional point feature, but the objects can be two-dimensional, three-dimensional. So on the picture B, we can see the image of a two-dimensional object. Same with the picture C, where we have this arrow that's being reflected and is producing the mirror image. And we have here two distinct light rays in the picture C that are an example of how the light rays are being reflected and producing the mirror image of a specific object. And finally, in the picture D, we have somewhat more complex type of a problem where we have two mirrors, mirror M1 positioned in a horizontal plane, and then we also have a mirror M2 that's positioned in a vertical plane. If we have that type of optical systems that consists of multiple mirrors, these multiple mirrors will be producing multiple images. So we can see here that these two mirrors M1 and M2 are producing multiple images of the single object. So we have one single object at point O, and we have three mirror images, mirror image I1, I2 and I3 that are produced by these two mirrors. Let's take a little closer look into how a mirror image is formed in a planar mirror. What we have here is an original object that's positioned at point S, and we also see our eye, and we can see a whole bunch of diverging light rays that are originating from our object. What do we mean by diverging light rays? We can see that these reflected light rays are diverging, meaning they are spreading out. They're kind of moving farther away from each other. So how we are using the ray tracing method, we are creating a whole bunch of light rays, incident light rays that are originating from our original object at point S, and then at each of the reflecting points along the surface of the mirror, we are applying the law of reflection and creating reflected light rays that are diverging. Next step, we are going to take all of these different reflected diverging light rays and we are going to extend them beyond the mirror, and you can see that all of these extensions, all of these dotted lines that have been constructed by extending the diverging reflected light rays beyond the mirror are going to eventually converge onto one single point that's labeled here as S prime. So that single point S prime is actually the position, is the location of the mirror image of our object positioned at point S. So our eye is able to see a point image at S prime in exactly the same way it would see a real point object placed there. It's also important to mention that the actual light rays do not exist behind the mirror surface that's represented by these dotted lines. So these dotted lines are not the actual light rays, but they're extensions. So since the image is created by light rays that are not real, we say that this mirror image is virtual. In other words, it cannot be projected onto a screen as in the case of a real image. So you're going to learn as we are moving through the material of this lecture and some of the subsequent lectures is that images can be either virtual or real, and in this specific case of a planar mirror, the images are virtual as already explained. If you have a more complex type of object, then you're going to be tracing its mirror image point by point. In other words, you're going to take some of the points of the object and you're going to be mirror imaging them to the mirror similar to the previous slide. So each object point has its corresponding image point along its normal to the mirror surface and as far below the reflecting surface as the object point lies above the surface. So in other words, the mirror surface serves as the plane of reflection. And it is important to note that the image position does not depend on the position of the eye. The construction also makes clear that the image size is identical to the object size, giving a magnification of unity. This applies to the planar mirrors. So if you have a planar mirror, the size of the image and size of the objects are the same. In other words, the magnification that is basically a ratio of the size of the image to the size of the object. In this case is equal to 1 because the size of the image is not larger or smaller relative to the object. It's also important to mention that the transverse orientations of the object and the image are kept the same. However, a right-handed object would always appear left-handed in its mirror image. Here's an interesting case of a mirror that does not lie directly below the object. The question is how to analyze this case. You would want to extend the mirror as shown in the picture, and this extension is going to enable someone to determine the position of the image as seen by an eye positioned to receive reflected light rays originating at the object. So even though there is no mirror immediately below the object, if your eye is positioned here, you're going to still see the mirror image of this object. And the way how you can explain that, how you can construct the position of the mirror image is again by extending the mirror and then using ray tracing technique. We have already shown the example of two mirrors. So we are talking about an optical system with two mirrors, one being positioned in the horizontal direction labeled as M1 and another one positioned in the vertical direction and labeled as M2. So this figure illustrates multiple images of a point object at a point O that are formed by these two perpendicular mirrors M1 and M2. As you can see, by using ray tracing method, we determining the three mirror images where the mirror image I1 is created by the mirror M2, and then mirror image I2 has been created by the mirror M1. And then we also have the third mirror image I3 that's formed by sequential reflections involving both mirrors. Here's an example that I would like you to work as a homework assignment. So you would want to make use of the law of reflection similar to the previous slides. and draw the image of the letter L as shown in the figure below in the mirror that's labeled as M. So again, you would want to construct the mirror image of this object in the shape of a letter L through the mirror M using the law of reflection and ray tracing techniques that have been explained on the previous slides. Here are the instructions on how to solve this problem. So what you want to do is you would want to define critical points along the object. So this L-shaped object has basically 4 critical points labeled as A, B, C, D that are vertices of the object. So for each of these different points, you are going to look at these points as single objects that are to be reflected. So you would want to find the mirror images of each of the points A through D, and that's what's been done on this figure here. So we define the points A prime, B prime, C prime, and D prime as mirror images of our points A through D, and then connecting them is forming the shape of the mirror image of our L-shaped objects. So to summarize the image forming in the plane mirrors, we can conclude that each ray of light that's incident on a planar mirror from a point of an object obeys the law of reflection. A point source of light in front of a mirror forms a virtual image because it is behind the mirror. And finally, the plane mirrors form virtual images that are of the same size as the original. In other words, the magnification is unity. Let's now focus our attention to different type of mirrors, so-called spherical mirrors or curved mirrors. So these mirrors are not positioned in a plane, but rather they are curved. They are part of a spherical shape. We are mentioning here 2 different types of spherical mirrors. On the left-hand side, you have so-called concave mirror, and then on the right-hand side, you have so-called convex mirror. These types of spherical mirrors have found many different applications. One of them, very popular one, is to create the wider angles in the traffic, as you can see in the picture on the bottom left-hand side. The mirrors that you have on your car, they are also curved so that they cover blind spot angles. So they have found many different applications, and it's very important to understand the way how the light is propagating through these types of mirrors, and that's what we are going to do on the slides that follow. The first, we are going to analyze these mirrors using Graphical Ray Trace method. In order to use the Graphical Ray Trace method, we have to establish certain terminology here. Number 1, we are always going to assume that the original objects are positioned on the left relative to the mirror. In other words, the direction of the incident light is always going from the left and then hitting the mirror on the right. We also are establishing the axis of the symmetry that's normal to the mirror surface. You can see here this axis of the symmetry. It's also called the optical axis. And then the point where the optical axis meets the mirror, that's labeled in our case V, is so-called vertex. We also have a center of the curvature of the mirror, which is the point C. So the point C, in other words, is the center of the big sphere that this mirror is laying on. And finally, we also have something called a focal point. The focal point is a point that's halfway between the center of the curvature and the vertex. We are going to see that all the parallel rays that are parallel to the optical axis will be reflecting in a direction that's going to be passing through the focal point. We already mentioned that there are 2 different types of spherical mirrors, namely convex and concave mirrors. In the case of a concave mirror, the outer edges of the concave mirror always curve towards the oncoming light. Such mirrors have their center of curvature C and the focal point F to the left of the vertex. Again, under the assumption that the incident light is coming from the left to the right, you can see that both the center of the curvature C and the focal point F of a concave mirror are positioned to the left relative to the mirror. And then you can also see that the outer edges of this mirror are curving towards the light, towards the incident light. In the case of a convex mirror, shown here on the right-hand side, the outer edges are curving away from the oncoming light. So here's the direction of the incident light, and you can see that the edges, both on the top and on the bottom, are curving away from the incident light. Their center of the curvature and the focal point are located to the right of the mirror. So that's how you can recognize or distinguish between the concave mirror and a convex mirror by using the terminology and definition as explained on this specific slide. Okay, let's now explain how we can trace a light rays through a concave mirror. So this is a very important slide. You're going to be tested on this. So it's very important to fully understand the technique of a ray tracing, which is the graphical technique used to establish the mirror image of an object in the case of a concave mirror. So what we have here is a picture. You can see a concave mirror here. And again, our assumption is that the object is positioned on the left relative to the concave mirror. And we want to figure out if this object is located at this location as shown, where is the mirror image going to appear in the case of a concave mirror. We are going to analyze 3 distinct light rays that are labeled here as light ray 1, and then we have a light ray 2, and finally we have a light ray 3. So these 3 light rays, 1, 2, and 3, they are originating from our object. So here we define the point P, that's the tip of our object, and we want to see where is going to be the mirror image of this point P. And again, to figure that out, we're going to be using these 3 distinct incident light rays, 1, 2, and 3. How did we come up with the light rays 1, 2, and 3? Light ray 1 is a light ray that is propagating in parallel to the optical axis. So you can see the optical axis here in the middle, that's perpendicular to this concave mirror, and then light ray 1 is propagating along the line that's parallel to the optical axis. When this light ray 1 hits the mirror, it's going to get reflected through the focal point. So that's the rule that you're going to apply when you're doing this type of analysis. So each time you have a light ray that's parallel to the optical axis, it's going to get reflected through the focal point F. And then we have another light ray that's labeled here as light ray 2, and you can see that this light ray 2 is propagating to the point F, to the focal point F. And that light ray that is incident through the focal point F, it's going to get reflected along the line that's parallel to the optical axis. Once more, light ray 2 that is moving to the focal point is going to get reflected along the line that's parallel to the optical axis. And then finally, the third distinct light ray is the light ray that is propagating to the center of the curvature C. That light ray is going to get reflected back along the same line through the center of the curvature. That's how you're going to be approaching the analysis of the concave mirror. So you would want to construct these 3 incident light rays, one that's parallel to the optical axis, one that goes through the focal point, and one that goes to the center of the curvature. And then you need to remember that the one that's parallel to the optical axis is going to get reflected to the focal point. The one that is moving through the focal point is going to get reflected parallel to the optical axis. And finally, the third one that's propagating through the center of the curvature is going to get reflected back along the same line. Once you constructed these 3 reflected light rays, you're looking at the point where they are intersecting. And you can see that the reflected light ray 1, and then reflected light ray 2, and then the reflected light ray 3 are intersecting exactly at this point here. So that's the only point where they intersect, and that actually defines the point which represents the mirror image of our point P. So that's our point P prime that is going to define the mirror image of our object that's positioned at the point P. So the procedure to establish the mirror image in a concave mirror again is to construct the 3 light rays, one that's parallel to the optical axis, one that's going to the focal point, one that's going to the point C, and then to reflect them correspondingly, where the one that was parallel to the optical axis got reflected to the focal point, one that was moving to the focal point got reflected parallel to the optical axis, and finally the one that went through the center of the curvature got reflected along the same line. Once you constructed the reflected light rays, you're looking at the point of intersection that is going to represent the mirror image of our object. Another important thing to mention is that we see the image appearing here on the left relative to the mirror. And if the mirror image appears on the left relative to the mirror, we are talking about the mirror image that's real, as opposed to the virtual mirror image that would be behind the mirror. So every time your mirror image appears in front of the mirror, we are talking about the real image that can be captured on the screen. The next that we want to cover is the ray tracing technique in the case of a convex mirror. What you can see here in the picture on the right hand side is a convex mirror. We have an object positioned at a point P, and we want to figure out where is the mirror image of this object. You are following the similar procedure as in the case of a concave mirror. In other words, you're going to construct 3 incident light rays, one that moves parallel to the optical axis, which is this light ray labeled as 1, and then the second one that's moving in direction of the focal point. Now keep in mind that focal point is behind the mirror, but still you want to establish this line that moves towards the focal point F. Obviously that incident light ray that's moving in direction of the focal point is not going to go all the way to the focal point, as it's going to eventually hit the mirror. And then finally the third one, the third incident light ray is labeled here as 3, is the one that's moving in direction of the center of the curvature. So both the light ray 2 and the light ray 3 are not going to go all the way to the center of the curvature and the focal point, but eventually are going to hit the mirror and are going to get reflected. Now what you can see here that we are following the same rules. So the incident light ray that's parallel to the optical axis is getting reflected along the line that's passing through the focal point. You can see this reflected light ray here, 1 prime. And you can see that is along this line that is passing through the focal point. So again, incident light ray parallel to the optical axis is going to get reflected along the line that's passing through the focal point. And then the light ray 2 was moving in direction of the focal point. When it hits the mirror, it's going to get reflected along the line that's parallel to the optical axis. And finally, the third light ray 3 that is moving in the direction of the center of the curvature is going to get reflected along the same line. So what you're observing here is 3 reflected light rays, the 1 prime, and then the 2 prime, and the 3 prime. What you can see that these 3 reflected light rays are diverging from each other. In other words, they are moving farther away from each other as they are moving farther from the mirror. So the mirror, you're looking for the point of intersection. Obviously, that point of intersection is not going to take place in front of the mirror. What you need to do is you have to extend beyond the mirror. You have to extend these 3 reflected light rays behind the mirror. And you can see here these dotted lines that are the extensions of the reflected light rays, and you can see that they are intersecting at one point labeled here as point P prime that is going to define our mirror image. So in this case, the mirror image is appearing behind the mirror or to the right relative to the mirror. In this case, we are talking about so-called virtual mirror image, since this mirror image is appearing behind the mirror. You cannot put the screen behind the mirror to capture this mirror image. Okay, now that we learned how to form the mirror images in a concave and a convex mirrors using ray tracing or graphical technique, let's shift our attention to yet a different type of a technique that can allow us to figure out the location and the size of the images in a concave and convex mirrors, namely analytical technique. So here we are going to be using the math, we are going to be using the calculations and specific formulas to accomplish determining the location and the size of the mirror images. The formula that we are going to use is so-called mirror formula, or so-called spherical mirror equation that's shown here on the bottom of this slide. You can see here 3 quantities showing up in the formula, quantities small p, small q, and small r. Let's define what these quantities are. The small p represents the distance of the object or original from the mirror. As you can see here on the picture on the right hand side, we have the original located at point O. So if you measure the distance between the point O and the vertex or the mirror, this distance that's shown here or labeled as small p is showing up in our mirror formula. The small q represents the distance of the image. So if you use the graphical technique or ray tracing technique, the image is going to appear eventually at a certain location. So here we assume that that location is a location here that's labeled as a point I. So if you measure the distance from the point I, which is a representation of the mirror image, to the mirror, that distance is shown here as Q, and that's what's showing up in this mirror equation. And finally, we also have a small r that represents the radius of this curvature. So if you're measuring the distance from the point of this curvature C all the way to the mirror, that distance is equal to the small r. So that's what's the meaning of these three quantities, small p, small q, and small r, that are showing in a mirror formula. And this is going to be applicable to any kind of convex or concave mirror, which is a good news. However, there's a caveat to this. We have to also talk a little bit about the sign convention on the next slide, because the sign convention has to be properly applied for a specific type of a mirror. Okay, so here are the sign convention rules for the mirror formula. Number one, the object and image distances P and Q are both positive when they are located to the left of the vertex, and both negative when they are located to the right. So for example, in the case of a convex mirror, you could see that the distance small p is located to the left relative to the mirror. That's why this distance, whatever it is going to be taken with a positive, with a plus sign. As opposed to, in this case, the distance q, you can see that the distance q is positioned right relative to the mirror. That's why this distance here, whatever it is to be taken with a negative or minus sign. The second rule pertains to the radius of the curvature r. If the center of the curvature C is positioned on the right hand side relative to the mirror, we are going to be taking the radius of the curvature r with a negative sign. And if the center of the curvature is positioned to the left relative to the mirror, we are going to take the radius of curvature with a positive sign. So in other words, both the P and Q and R all follow the same rule. As long as they are positioned left relative to the mirror, they are taken with a positive or plus sign. And if they are positioned behind the mirror or on the right hand side relative to the mirror, then we are going to take them with the minus sign. The next is about the dimensions. The vertical dimensions are to be taken positive if they are above the optical axis. So for example, if your object is positioned here above the optical axis, this is our optical axis. So if your object is here, then you're gonna take its height with a positive sign. And if the mirror image appears, for example, below the optical axis, then the size or that vertical dimension is going to take it with a negative sign. The focal length follows the same rule as the radius of the curvature. So if the radius of the curvature is positive, then the focal length is also going to be taken positive. And also if the radius of the curvature is negative, then the focal length are also taken as negative. We also assume that light is always directed from the left to the right. And finally, according to this sign convention, the positive object and image distances correspond to the real objects, while negative object and image distances correspond to the virtual objects and images. You may have probably noticed that in the case of a curved mirrors, the object size and the image size are not the same. So in this case, we are not talking about the magnification that's equal to the unity, but the magnification can be either smaller than 1 or larger than 1. So how do we calculate the magnification in the case of a curved mirror? Magnification is going to be defined as the ratio of the size of the image relative to the size of the object. So in this specific case that you're seeing here on the right hand side, you can see that the image is smaller than the original. In other words, if you take the size of the image and divide it by the size of the original, that ratio, which represents the magnification, is going to be smaller than 1. There's a few other ways how you can calculate the magnification. You can also use the formula that's shown here on the bottom left hand side. So you can look at the P and Q. Remember how we defined the P and Q. The P represents the distance of the original from the mirror, and Q represents the distance of the image to the mirror. So if you take the ratio of Q over P with the negative sign, you can come up with the value of the magnification. So once more, magnification M is defined as the image size divided by the object. The sign convention for the spherical mirrors must be taken into account when you're doing the calculation and applying the formula on the bottom. And another important thing to remember is when M is positive, the image is erect, meaning it's going to be above the optical axis, and when the value of the M is negative, then image is inverted. In other words, it's going to be positioned on the opposite side of the object relative to the optical axis. So those are important rules that need to be remembered that you're going to be tested on. So you need to know that if, again, the magnification is positive, then both the object and the image are going to appear at the same side of the optical axis. If the M is negative, then the object and image are going to be appearing on the opposite sides of the optical axis. And then also if M is larger than 1, that would mean that the image is larger than the object. And if M is smaller than 1, that would mean that the image is smaller than the object. All those rules have to be memorized and remembered because, again, I'm going to be asking you the questions of that nature on the tests. So here's an example that we would want to analyze and apply all the rules of the mirror formula and sign convention. And also we would want to apply the graphical ray tracing technique to solve this problem. So here we have a mirror stick positioned along the optical axis, and you can see that two toy figures are positioned at two ends of this mirror stick. They are 5 centimeters high and they are both erect, so they stand above the optical axis. So the questions that are asked in this problem is how long is the virtual image of the mirror stick, and then also how tall are the toy figures in the image. Are they both erect or inverted? So let's look how to solve this problem. Okay, so let's use the analytical method to solve this problem. As you can see in this problem we have two toy figures, one at a farther distance away from the mirror and one that's closer to the mirror. So we are going to label the toy figure that's farther from the mirror as a toy figure A, and then the toy figure that's close to the mirror is going to be labeled as a toy figure B. So for both of the toy figures A and B, we are going to figure out the distance away from the mirror. As we can see, for the case of the toy figure A, the distance away from the mirror is going to be equal to 100 plus 60 centimeters, which is 160 centimeters. And then for the toy figure B, the distance is equal to 60 centimeters. And according to the sign convention, both of these are to be taken with a positive sign since both toy figures are positioned left relative to the mirror. We also know that the focal length of the curved mirror is equal to 40 centimeters. In other words, the radius of the curvature is equal to 80 centimeters, and both the focal length and the radius of the curvature are to be taken with a negative sign because the center of the curvature and the focal point are positioned on the right side relative to the mirror. So our R is going to be equal to minus 80 centimeters, or our focal length is equal to minus 40 centimeters. Now let's apply the mirror formula to the case of the toy figure A and toy figure B. So here we can use the calculator to calculate these two fractions. So 1 over 160 is 0.00625. and 1 over 40 is 0.025. So here we can calculate the value of 1 over QA by extracting it. So if we add these two negative numbers, we get 0.03125. And then here we can reciprocate the two to come up with a QA. So QA is going to be equal to minus 1 over 0.03125, which is equal to negative 32 centimeters. So this tells us that the toy figure A that was farther away from the mirror is going to produce the mirror image that is going to be 32 centimeters away from the mirror, and the fact that the Q is negative means that this mirror image is going to appear to the right relative to the mirror. We can repeat the same calculation for the toy figure B. Okay, so here's the whole calculation for the toy figure B. So we pretty much apply the same procedure as the toy figure A, with the only difference that the distance of the toy figure B is equal to 60 centimeters. So the calculation is pretty much the same. So we came up with the value of Q of 24 centimeters. Now, what's the meaning of these two values? So again, the 32 centimeters is the distance of the mirror image of the one toy figure, and then 24 is the distance of the second of the mirror image of the second toy figure. So we can conclude that since the first toy figure is 32 centimeters and the second figure is 24 centimeters, means that the mirror images of these two toy figures are about 80 centimeters away from each other. So the mirror images of the toy figure A and toy figure B are equal to 8 centimeters. So the distance of mirror images is 8 centimeters. What we can do here as well is we can also calculate the size of these two mirror images using the following formula. So we can figure out the magnification as a negative Q over P. So for the toy figure A, we have negative of QA, which is negative 32 over P, which is 160 centimeters. So if you do this math here, you come up with 32 over 160, which is equal to 0.2, positive 0.2. And then for the toy figure B, you can do the same math, minus QB over PB is equal to negative 24 over 160, which is equal to plus, let's see, 24 over 160 gives us 0.15, plus 0.15. Now let's analyze what is the meaning of these two values. Number one, both of them are with a positive sign, which means that they are going to be positioned on the same side relative to the optical axis as the originals. So since the two toy figures are above the optical axis, this means that the mirror images are also going to be above the optical axis. That's number one. And then number two, you can see that the magnification is less than 1, which means that the mirror images are going to be smaller than the originals. So the first mirror image of the first toy figure A is going to be equal to 20% of the original, while the second toy is going to produce the mirror image that is going to be 15% of the size of the original. Here's a few examples of applications of the mirrors. So the mirrors are applied in telescopes. You can see here on the right hand side a huge Hale telescope that's 200 inches long. It's located on the Mount Palomar. And then here on the left hand side you have a few examples of telescopes as well. The one known as a Cassegrain telescope. You can see the picture of it here on the bottom. And then the whole optical system that's within this telescope is shown here in the picture on the top. You can see that this type of a telescope consists of a small convex mirror and then also a large concave mirror. So it's a complex optical system that allows us to see small objects that are far away from us. Found applications in many different fields, especially in astronomy. If you want to take a closer look at this type of a telescope, you also are given a math problem here where you would want to analyze the way how the light is passing through this type of optical system with specific types of information that is given in this math problem. So this math problem is given as a home assignment for you to take a look at. So to conclude this lecture number 2, we have analyzed an important optical component used in many optical systems, namely a mirror. We learned how to analyze the propagation of the light through mirrors. We introduced 2 different types of techniques, one being a graphical technique or so-called ray tracing method, and then the second one being an analytical approach that uses so-called mirror formula. So both of these techniques would have to produce the same result through 2 different means. And finally, at the end of this lecture, we looked at a few applications of the mirrors, specifically in telescopes. With this, I'm going to conclude the lecture number 2 in our series of geometrical and physics optics lectures, and I'm going to see you next time.